first question I have here is, it is impossible for a game to have two Nash equilibria, true or false? A few people are saying false. Great. Okay, so the answer is false. And we can think of a particular game that we covered in the class slides that actually gives us a game outcome with two Nash equilibria. And that game was the chicken game. And the other version in the slides was the hawk and dove game. So what we have in the chicken game is we have two players, player one and player two. We always put player one on the row and player two on the columns. And so these two players have the same two strategies. Either they can swerve or they can continue straight. If they both continue straight, they're going to have a head-on collision. And so there is going to be a huge cost to this. So the outcome in this case is going to be a large negative payoff to both players. If they both swerve, well, they're going to walk away without any injuries, except to their pride. Because the game of chicken is supposed to establish whether or not you are brave. Can you continue straight for the longest time possible? If player one goes straight and player two swerves, we would say that player one has won the chicken game and player two has lost. So the penalty to losing the chicken game is not as large as the penalty to having a very serious accident if you hit someone head on. And then in this outcome here, where player one is swerving and player two is going straight, player two is the victor and player one is the loser. So these were the payoffs in that game. How we solve all of our games in Unit 4 is we use what we call best response solutions. So what we mean by a best response is it is the response or the choice of strategy to the other player's strategy that gives you the higher possible payoff. So how we solve with best responses is we say, okay, what if player one considers that player two is going to swerve? In other words, let's imagine a scenario in which player two is swerving. What would player one's best response be in a world in which player two swerves? If player one swerves, they're going to get 0. But if player one goes straight, they get 1. So the higher payoff to player one comes from playing straight. So straight is a best response for player one to player two playing swerve. So I always underline best responses because this really helps to find the Nash equilibrium solution. Okay, now we're going to imagine a world in which player two is playing straight. In this outcome, or in this sort of world, if player one goes swerve whilst player one plays straight, player two plays straight, he's going to get a payoff of -1. If player two plays straight and player one plays straight, they're going to get a payoff of -1,000. So -1 is better than -1,000. So the best response of player one to player two playing straight is to play swerve. So what we can see from this situation here is that player one does not have a dominant strategy. What we can see in this game is that player one's choice of strategy depends on what player two does. There isn't something that player one does irrespective of what player two does. So those are the two best responses of player one. We do the same thing for player two then. So what we say is, let's imagine that player one is going to swerve. What would player two's best response be to player one playing swerve? If player two swerves, they get 0. If player two goes straight, they get 1. So player two's best response to player one swerving is to play straight. So I underline the best response. Then if player two believes player one is going to play straight, If they play swerve, they're going to get a -1 payoff. And if they play straight, they're going to get a -1,000 payoff. And so the best response of player 2 to player 1 playing straight is to swerve. And so we have exactly the same situation with player 2. Player 2 doesn't have a dominant strategy. Player 2's best response strategy also depends on the choice of player 1. So how do we find Nash equilibria? We find Nash equilibria through game outcomes in which both players are playing best responses. And that's why I underline best responses, because now I can see that in this outcome here, both of them play a best response. And in this outcome here, both players play a best response. And so this game has 2 Nash equilibria, and these Nash equilibria are straight, swerve. So this describes the outcome here, because we always write player 1 first. And then the second Nash equilibrium is swerve, straight. And that is this outcome over here, swerve, straight. So this type of game proves that it is possible for a game to have 2 Nash equilibria. And that is why the answer to question 1 is false. So question 2 says, players in a repeated game may be able to solve social dilemmas. So let's put it to the chat. What do we think the answer to this question is? True or false? Players in a repeated game may be able to solve social dilemmas. Great. Okay, we have a lot of truths, and that is absolutely correct. So the answer to this is true. So if 2 players are playing a game and they end up in a suboptimal outcome, so we can actually do it with this game over here. So let's prove that question 2 is true using question 3, because that's going to help to solidify the idea of repeated games. So we have this game, and the question is asking, is this game an example of the prisoner's dilemma game? So there are a few things that characterize the prisoner's dilemma game. The first thing is that both players have dominant strategies. So a prisoner's dilemma game is a game in which the Nash equilibrium is a dominant strategy equilibrium. In other words, these 2 players are going to do the same thing no matter what the other person does. So irrespective of the other person's choice. And the outcome is suboptimal. We also can call this a social dilemma. But as we saw in Unit 5, there is another more technical definition of a social dilemma, which I'll go through in some subsequent questions. Okay, so prisoner's dilemma, both players have to have dominant strategies, and the outcome is suboptimal. So if we solve this game using best response strategies, are we going to find an outcome that is suboptimal? And are we going to find that both players have dominant strategies? So if Jemima, who is player 1, the role player, believes that Sam is going to wear a mask, then her best strategy is to not wear a mask. Because if Sam wears a mask and Jemima wears a mask, her payoff is 5. But if she doesn't wear a mask, her payoff is 6. So the best response is underlined. If Sam is not going to wear a mask, then Jemima has a best response to also not wear a mask, because 3 is larger than 2. And so what we find is that Jemima does have a dominant strategy. So Jemima has a dominant strategy. And the way we define a dominant strategy is that it's something that that player will do irrespective of what the other player does. She will always choose to not wear a mask irrespective of what Sam does. Okay, so Jemima has a dominant strategy. We then look to see whether or not Sam has a dominant strategy. So if Sam believes that Jemima is going to wear a mask, then Sam would get 5 if they wear a mask and 6 if they don't wear a mask. So not wearing a mask is a best response to Jemima wearing a mask. And if Jemima doesn't wear a mask, then Sam's best response is to also not wear a mask. And so at the end of the day, the same thing applies to Sam as well. Sam also has a dominant strategy. So the first condition of a Prisoner's Dilemma game is met. Both players in this game have dominant strategies. The outcome of this game is going to be don't wear a mask, don't wear a mask, because this is where we find 2 best responses being played. So now we have to establish, okay, is this suboptimal? And we can see that, yes, this is suboptimal, because if they both chose to wear a mask, both of them would be better off. So the second condition for a Prisoner's Dilemma game is met. And so we can say, true, this game is an example of the Prisoner's Dilemma game. Okay, so how could repeating this game solve the social dilemma? Well, if after playing this game, they realize, because they have all the information available to them, and what we assume is that this is a one-shot simultaneously played game where they're making choices independently. But if they're able to repeat this game and they're aware that, you know what, if we actually coordinate and choose to both wear a mask, we can both be better off, then that would help to solve this social dilemma. This is suboptimal for this society of 2 people. If they had chosen instead to both wear a mask, they would have ended up making higher payoffs. But the reason they end up here is because self-interested behavior and taking these decisions independently. So not taking the decisions in a coordinated way, not being able to discuss beforehand, what are you going to do so that we can try and find the optimal outcome. What we find is that by being driven by self-interest, they will, through best responses, end up here at a suboptimal outcome. But if they could repeat the game, or they could coordinate in some way, they would be able to find themselves at an optimal outcome of both wearing a mask. Is there a Nash equilibrium in the Prisoner's Dilemma? Yes, this is a Nash equilibrium. So the important thing to remember is the follows. A Nash equilibrium occurs where both players are playing a best response strategy. That's the same as us saying that when we are in a Nash equilibrium, neither player has an incentive to change their strategy because their strategy is a best response to what the other player is doing. If the best responses in this Nash equilibrium are dominant strategy responses, so our dominant strategies, then the Nash equilibrium is a dominant strategy equilibrium. So what we can take away from that is that all dominant strategy equilibriums are Nash equilibriums, but not all Nash equilibriums are dominant strategy equilibriums. And we can see that in the chicken game. In the chicken game, these are Nash equilibria because both equilibriums involve 2 best responses being played. But neither of these are dominant strategy equilibriums because neither player has a dominant strategy. Okay, So all dominant strategy equilibriums are Nash equilibriums, but not all Nash equilibriums are dominant strategy equilibriums. Okay, so this is the question from A1. Just gonna make the zoom a little bit better. So in question 4, we get given the following information. Thandi and Johan get arrested by the police as suspects in a crime. They must decide to confess or not to confess. The number of years they will spend in jail, given the strategy that they choose, is given in the table below. Okay. Assume that they are playing a simultaneous one-shot game with no cooperation possible. Which of the following statements is true? So we're trying to find which of A, B, C, and D is a correct statement with reference to this game. So answer A says, neither player has a dominant strategy. So what you need to do is solve the game in order to establish whether or not anybody in this game has a dominant strategy. So same process as before. Every single game you solve in this way. If we believe that Johan is going to confess, then Thandi has a decision to either confess or not confess. And what we see is that her best option is to confess. Why is that the best option? Less years spent in jail. Perfect. Okay, so if Johan confesses and Thandi confesses, she's only going to go to jail for 4 years. But if she didn't confess, she would go to jail for 8 years. So her best option is to confess. Great. Okay, now if Johan chooses to not confess, then Thandi would go to jail for 1 year if she confessed and 2 years if she didn't confess. And so Thandi's best response to Johan not confessing is to confess. So Thandi has a dominant strategy. So Thandi has a dominant strategy to confess. And because we can prove that Thandi has a dominant strategy, A has to be incorrect. Because as A says, neither player has a dominant strategy. And what we've just proven is that Thandi does. Okay, we can show also that Johan has a dominant strategy as well. So if Johan believes that Thandi is confessing, then Johan's best response is to confess, because 4 is less than 8. If Thandi is going to not confess, then Johan's best response is also to confess, because 1 is fewer years in jail than 2. So we find that Johan also has a dominant strategy to confess. So Johan has a dominant strategy to confess. And so in this game, we end up with a Nash equilibrium that is also a dominant strategy equilibrium, because in this Nash equilibrium, both players' best responses are dominant strategies. So we go to B, C, and D. B says both players can do better if both do not follow their dominant strategy. If they had to choose both not to confess, we would end up in this equilibrium here where they're only getting 2 years in jail each. So yes, both players can do better if both of them chose to choose the strategy not confess. Okay, then C says the outcome confess is the optimal outcome for the players of this game. That is incorrect, because the optimal outcome for this game is both of them going to prison for only 2 years. That would be a better social outcome for these two people. Okay, so C is wrong. D, the Nash equilibrium of this game is Pareto efficient. So this is now bringing in a little bit of unit 5. So what do we mean by Pareto efficient? When we are in a Pareto efficient outcome, it means that there are no Pareto improvements possible. And what that means is that it is impossible to make one person better off without making the other person worse off. So if we look at the Nash equilibrium of this game, both of them are going to prison for 4 years each. There is a Pareto improvement possible on this outcome. This outcome over here, where both go to jail for 2 years each, is an improvement for both players. So if we had to move from this allocation, this outcome to this outcome here, both players would be better off. And so because this outcome exists, it makes this outcome Pareto inefficient. There are Pareto improvements possible. So this is wrong because the Nash equilibrium of confess is actually Pareto inefficient. The don't confess outcome would make both players better off. And that defines a Pareto improvement. So question 5 involves 2 players, Troy and Abed, and they need to bring one type of snack to a party. They both favor pizza, but they generally prefer to have a variety of party food rather than eating only pizza. The payoff matrix below represents their strategic interaction. Which one of the following statements is incorrect? Okay, so now we're looking for a wrong answer or a false statement. So A says pizza is Pareto dominated by popcorn donuts. Okay, so let's take a step back. What do we mean by Pareto dominated? If an outcome, so if one of these outcomes, Pareto dominates another outcome, it means there is a Pareto improvement. In other words, if pizza Pareto dominates popcorn donuts, that means that both players do better, or at least do no worse, in pizza than they do in popcorn donuts. So if we look at the outcome here, pizza has the payoffs 2-2, and popcorn donuts has the payoff 3-3. So based on what I just said, would you say that pizza represents a Pareto improvement over popcorn donuts? Or is the converse actually true? Is it actually true that popcorn donuts is a Pareto improvement over pizza? Popcorn donuts would make both of them better off than pizza. So popcorn donuts is a Pareto improvement over pizza, which means that A is correct. Okay, pizza is Pareto dominated by popcorn donuts. Okay, everyone agree with that? And because it's true, it makes it incorrect in the context of this question. Okay, so popcorn donuts is a Pareto improvement over pizza. So pizza is Pareto dominated. So that's wrong. There are 3 Pareto efficient outcomes in this game. Okay, this is a tough one. I'm going to represent this game in a graph. So this is how Unit 5 looked at these games that were presented in Unit 4. So we have Troy and Abed, and they can make anywhere between 2 and 3 utils. So this is 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay. Then in the outcome pizza, they both make 2. So that's the pizza. Then with pizza donuts, so if Troy brings pizza and Abed brings donuts, Troy gets 4 and Abed gets 5. So that's going to be over here, 4, 5. So this is pizza donuts. And then when it's popcorn pizza, then it's going to be 5, 4. So this one here is popcorn pizza. And then popcorn donuts is 3, 3. Popcorn donuts, POD. Okay, so that's popcorn donuts. So A said pizza is Pareto dominated by popcorn donuts. If I look at this picture here and I take a vertical line up from pizza and I take a horizontal line from pizza and I shade in this region that is contained by both of those lines. What that region represents are all of the allocations, so all of the outcomes of this game that Pareto dominates pizza. The reason why all of these other outcomes Pareto dominate pizza is because in popcorn donuts, both of them are better off than in pizza. In other words, this outcome here doesn't make anyone worse off than pizza. If anything, it makes everyone else better off. The same with pizza donuts. Pizza donuts, Pareto dominates pizza because both of them are better off here than they are there. So this is a Pareto improvement. And then the same thing with popcorn pizza. So pizza is Pareto dominated by popcorn donuts. And in fact, it's also Pareto dominated by popcorn pizza and by pizza donuts as well. Okay, so B said there are 3 Pareto efficient outcomes in this game. Okay, now Pareto efficient means, so if an outcome is Pareto efficient, it means there are no Pareto improvements possible, which is the same as saying that no other outcome Pareto dominates it. If an outcome is Pareto inefficient, then Pareto improvements are possible. And other outcomes Pareto dominates it. So what we can already establish from this picture is that pizza is inefficient because all other outcomes Pareto dominates pizza. So pizza, Pareto inefficient. Now let's look at popcorn donuts. So we do the same thing. We take a vertical line up from where that point is, and we take a horizontal line across, and we shade in the region in which that is contained by these 2 lines. And what do we find? We find that popcorn pizza and pizza donuts Pareto dominate popcorn donuts. So this outcome here of popcorn donuts has Pareto improvements possible over it. And so popcorn donuts is also Pareto inefficient because these other two outcomes Pareto dominated. So that makes B incorrect because there are only 4 possible outcomes of this game, and we've already established that 2 of these 4 outcomes are inefficient. So it can't possibly be that there are 3 Pareto efficient outcomes. In fact, there are only 2 Pareto efficient outcomes in this game. So popcorn pizza is not Pareto dominated by any other allocation, and pizza donuts is not Pareto dominated by any other allocation. And so these 2 outcomes are both Pareto efficient. Okay. C then says popcorn pizza. So this one here, popcorn pizza, is a Pareto efficient outcome. That is correct, which is why it is not the right answer to this question. Neither Troy nor Abed has a dominant strategy. Okay, so now we need to use best responses to establish whether or not there are dominant strategies in this game. So if Abed is going to play pizza, then Troy's best response is to play popcorn because 5 is more than 2. If Abed is playing donuts, then Troy's best response is to play pizza because 4 is more than 3. So Troy doesn't have a dominant strategy. Troy will play popcorn if Abed plays pizza, and he will play pizza if Abed plays donuts. We then look to see from Abed's perspective. Oof, I'm starting to wonder if I've actually... Yeah, so I've actually also just noticed that I might have just twisted myself up. Would that not make B correct in context of the question then? Yes, you're absolutely correct. See, this is what happens when we ask you questions of which is incorrect, because immediately then I think it's going to be the wrong answer. So B is incorrect, which makes it correct in the context of this question. Yeah. Thank you so much for pointing that out, Geordie. And yes, Rampedi as well. Okay, so yes, B is correct, because as I was just about to realize, D has to be incorrect because Troy doesn't have a dominant strategy. And if we play the best responses for Abed as well, we find that if Troy plays pizza, Abed would choose a best response of donuts. And if Troy plays popcorn, Abed chooses a best response of pizza. And so neither Troy nor Abed have a dominant strategy, which means D is a correct statement, which means it is not correct for this question, which is asking for an incorrect answer. Okay, question 6. So question 6 says, detectives Jake Peralta and Rosa Diaz are interviewing a suspect they've arrested for a string of robberies in Brooklyn and need to get a confession out of their suspect. Jake and Rosa can either choose to be empathetic or tough. Unfortunately, because the police station is very busy, they cannot discuss their approach with one another. So they will have to make this decision independently. Okay, so that's just setting up the problem as one in which it's a one-shot game where they're having to make their decision simultaneously, but they can't collaborate or cooperate on their decision. The interaction is represented by the table below. Which of the following statements regarding the game above are correct? Okay, this is much easier. It's not going to confuse me. So statement 1 says the Nash equilibrium of the game is tough and pathetic. Okay, so to find the Nash equilibrium of this game, we need to solve the game through best responses. This is why, as you can play this game many, many, many times, once you know how to solve it, you're getting it correct every single time. So if Rosa plays empathetic, Jake will play tough. That's the best response. If Rosa plays tough, Jake's going to be empathetic. If Jake plays empathetic, Rosa's going to be tough. And if Jake plays tough, Rosa will also be tough. And so what we find is that there's only one outcome in which both players are playing a best response, and that is the outcome empathetic tough. Okay, so statement 1 says the Nash equilibrium of the game is tough empathetic. Why is that incorrect? Remember, when we write out these outcomes, we always put player 1, then player 2. And player 1 is our row player and player 2 is our column player. And so the Nash equilibrium of this game is empathetic tough. It's the other way around. And so this is incorrect. Jake has a dominant strategy to be empathetic. So what we found is that Jake would be tough if Rosa is empathetic, but he would be empathetic if Rosa is tough. In other words, Jake doesn't have a dominant strategy. Jake does the opposite of whatever Rosa does. 3, this game represents a prisoner's dilemma. Does anyone want to tell me why this game doesn't represent a prisoner's dilemma based on what we did earlier? Jake doesn't have a dominant strategy. Awesome. Both don't have it. Awesome. Okay. So with a prisoner's dilemma, what we saw earlier is that in a prisoner's dilemma, both players have a dominant strategy. They're going to do the same thing no matter what the other player does. And so in this game, what we find is only Rosa has a dominant strategy. So this is incorrect. 4 then says Rosa has a dominant strategy to be tough. And that is true. That's correct. If Jake plays empathetic, Rosa's tough. If Jake plays tough, Rosa's tough. And so the answer to this question is C. Only statement 4 is correct. Somebody says it's also not suboptimal. Yes, you're absolutely correct. It isn't suboptimal. What would be the suboptimal outcome of this game? Can anyone see from the payoffs in the table which of these outcomes would be socially suboptimal for these two people, for this little society of two people? Awesome. Empathetic, because the total payoffs are 5. And if we compare this to tough, if we had to end up here versus here, Jake would be no better or worse off, but Rosa would be better off. So this is a Pareto improvement over this outcome here, because somebody benefits, but nobody has to lose for that benefit. I'm going to go to question 7, and question 7 uses one of these graphs. And this was from A1. So I feel like now, given everything we've covered, this should be fairly straightforward now. So we've got this 2-player game represented in graphical form. And the first question says, which of the following statements regarding the game is true? Okay, now, this is where we're kind of reversing things a bit. Here, we took a game that was in a matrix, so in table form, and put it in a graph. Here we have the graph, and my advice is to draw this in a table. And that's going to make this game, that's going to make this question a lot easier to solve. So all you need to do is draw yourself a really rough little matrix table. So we have player 2, player 1. We have yes, no as the 2 options. So I'm going to say yes, no, yes, no. And if both play yes, yes, then we would see, so I wonder if I didn't copy the values. Okay, so let's just make up some values here. So let's say this is 1, 2, 3, 4, and this is 1, 2, 3, 4. So it's not drawn to scale, but the thing with utility payoffs, right, is that they only need to show a ranking of outcomes. So this value here is definitely smaller than that value, is smaller than this value, is smaller than this value, and the same going up the vertical. So yes, yes gives player 1 2 and player 2 4. Okay. Then player 1 no, player 2 yes. So player 1 no, player 2 yes is 1 1. Player 1 yes and player 2 no is player 1 gets 3 and player 2 gets 2. And then no, no gives player 1 4 and player 2 3. Okay. So that might have been a little bit tricky. Can I go through that one more time? Would that be useful? Okay. So I'm just going to just quickly show you how I filled in those numbers just once more. So if player 1 plays yes and player 2 plays yes, player 1 gets 2. So the first number is player 1 and player 2 gets 4. So the second number is 4. If the outcome is player 1 plays no and player 2 plays yes, that's no yes, and they both get 1. If player 1 plays yes and player 2 plays no, that's going to be yes, no. So player 1 gets 3 and player 2 gets 2. And then if the outcome is no, no, player 1 gets 4 and player 2 gets 3. So that's how I end up with the game. Must player 2 be on the y-axis or does it not matter? It doesn't really matter, just as long as there's consistency between your picture and the table. So it won't matter too much for the game, but always make sure that when you plot the table, you have player 1 on the row and player 2 in the columns, because these allocations will always be written as player 1 first, player 2 second, player 1 first, player 2 second. Yes, and as Mr. Shoba says quite correctly, that usually when we have these XY plots, you would put X first and Y second. So plotting player 1 on the X-axis and player 2 on the Y-axis makes the most sense mathematically, and it makes drawing up this table a lot easier. Okay. Thank you so much, Ms. Witbooi, for answering questions. It really helps to be able to explain some of these things that I've already covered to other people in the chat. So I really appreciate that. Okay, so we have this table now. So we can solve it using best responses. If player 1 thinks that player 2 is going to play yes, they're going to play yes. If player 2 is going to play no, then player 1's best response is to play no. And so A states player 1 has a dominant strategy of no. And as we have just proved, that is not correct. That is false. Player 1 doesn't have a dominant strategy. They play yes when player 2 plays yes, and they play no when player 2 plays no. B then says this game has a dominant strategy equilibrium. Why would B be false based on our answer to A? So why would B be false given what we've just shown? At least one player doesn't have a dominant strategy. Both players don't have a dominant strategy. Perfect. Okay. So because we've already shown that player 1 doesn't have a dominant strategy, this game can't have a dominant strategy equilibrium, because a dominant strategy equilibrium means both players have dominant strategies. And in this case, player one doesn't. And so there can't possibly be a dominant strategy equilibrium in this game. C then says this game has two Nash equilibria. So in order to figure out whether that is true or not, we need to show what player two would do. So if player one plays yes, player two will play yes. And if player one plays no, player two plays no. And so, yes, there are two Nash equilibria in this game. The one Nash equilibrium is both play yes. The other Nash equilibrium is both play no. And so C is true. D then says the Nash equilibrium of this game is yes, no. That is incorrect, because as we've shown, the two Nash equilibrium of this game are yes, yes, and no, no. Okay, so the trickiest part of doing this is to take this graph and to put it in a table. It is much easier to take a table into a graph. It's a little bit trickier to take a graph into a table. But even if you weren't able to do this part of the question, you can do the next part, because the next part engages with Pareto efficiency and inefficiency, which is something we can do using just this picture. So for the next part of the question, it says, which of the following statements regarding the game is or are true? The outcome, yes, yes, is Pareto inefficient. So if we look at the picture, yes, yes is up here. And so in order for that to be inefficient, it means that some other allocation has to Pareto dominate it. And what we can see here is that no other allocation Pareto dominates yes, yes. And that means yes, yes is efficient. There are no Pareto improvements possible on yes, yes. And so statement one is incorrect. The outcome, yes, yes, is not Pareto inefficient, it is Pareto efficient. 2 says there are more than one Pareto efficient outcomes. Okay, so let's do the Pareto domination for all of these allocations. So for no, no, we find the same thing. No, no is Pareto efficient because no other allocations Pareto dominated. And so 2 is correct because yes, yes is Pareto efficient and no, no is Pareto efficient. And so there are more than one Pareto efficient outcome in this game. 3 then says, yes, yes is a better outcome than no, no. Does somebody want to take a chance at saying whether that is a true statement or a false statement? Yes, yes is a better outcome than no, no is false because we actually can't say. Okay. So if we take let's put it this way. If you are player two would prefer yes, yes, then no, no. Player one would prefer no, no to yes, yes. So it's not clear if we take the perspective of player two or player one, which of these is the best outcome or the better outcome. If we take the perspective of what are the total payoffs to these two people in this game, then we would say that no, no is better because no, no has a combined payoff of 7 and yes, yes has a combined payoff of 6. So using that reasoning, we cannot claim that yes, yes is a better outcome than no, no. And so 3 is incorrect. And so B is the correct answer to this question. Only 2 is true using the information we have. Geordie Payne says for combined utility, it is better, but not necessarily for no, no. Yes, so if we take combined utility into account, no, no is better. But if we had to ask these two players, they wouldn't be able to come to an agreement. Yeah. Okay, great. So that's question 7 done. And I'm just looking for my question 8. I printed my stuff out earlier and my pages are okay, so Ms. Kawaloka asks, so if yes, yes had a better combined utility than no, no, then the statement would be correct. Yes, that is absolutely true. So let's say yes, yes had payoffs 4-4, then yes, yes would be better than no, no. Because then not only would yes, yes be the only Pareto efficient outcome, but it would be better. So imagine this 2 is a 4. If these were both 4s, then no, no would no longer be efficient, because 4-4 over here would make player 1 no better or worse off, but it would make player 2 better off. And so if this had higher payoffs than this one here, it would change a lot about this game in terms of which is efficient and which isn't. We don't know their preferences. Can we say this is why it's false? Yeah, so let's say this question was asked as a descriptive question. So let's say the question was, explain if yes, which of yes, yes and no, no is a better outcome. In your explanation, what you could then say is that subjectively, if I think about these two people, it's very difficult for me to say which of these is better from the perspective of player 2 or player 1. But if I'm going to use the combined utility in each of these outcomes to say which of these is better, then we would say that no, no is the better outcome, because no, no results in a higher total payoff to the society than does the outcome yes, yes. Well, that's why I think there were no numbers initially, because total would be unknown. Yes, actually, that's a perfect statement to make. Yes, so the reason why originally this picture had no numbers is because at the end of the day, it is going to be difficult to say which of these is better if we actually don't know what these true numbers are. I just filled in rankings, to put it in those terms, just to make solving this game a little bit simpler. For people who rely on a table to be able to solve for best responses. But you're absolutely correct. In any case, yeah, that's why 3 would be incorrect, because we just actually don't know. There just isn't enough information. Is it possible for the total utility to be equal? Yes, it could be possible that these two allocations would provide the same total utility, and then we also wouldn't be able to say which is best. So because there's quite a lot of unknowns here, it is really difficult to say what is better in this game. All we can say with surety in this game is that these two outcomes are efficient. That's what we can say, because that's an objective truth, right? But subjectively, without further information, it would be really difficult, and in this case, impossible to say which is better. Thank you, Mr. Bernard, for adding that. That's absolutely perfect. Yes, there's just too many unknowns. So just to make sure, are we all okay with question 7? Again, remember, you are able to watch this back later. I'm just going to do a little bit of editing to the video, and then I will upload it later today. Okay, so let's move on to question 8. So this was in the descriptive section, so section 3, section C in A1. And this is an interesting question because C engages with how incentives are used to avoid social dilemmas. So I really like this question. So the question starts by telling us that it is the 2024 India Premier League cricket tournament, and the Delhi Capitals are set to face the Chennai Super Kings in the final. Assume that the two teams must choose whether to play tactically or aggressively, and their interaction is represented in the table below. What is the equilibrium outcome of this game? So exactly the same approach every time. We use best responses. So if Chennai Super Kings are going to play tactical, then the Delhi Capitals are going to choose to be aggressive. If the Kings are going to be aggressive, then the Capitals are also going to be aggressive. So the Capitals have a dominant strategy to play aggressively, no matter what the Super Kings do. Then, if the Super Kings believe that the Capitals are going to be tactical, they will play aggressive. And if the Capitals are going to play aggressively, then the Kings are also going to play aggressively. And so they also have a dominant strategy to play aggressively, no matter what the Capitals do. And so we have our Nash equilibrium is aggressive, because that is where we find two best responses being played. So the equilibrium outcome of this game is aggressive. So one mistake that students can make on this type of question is they can write the outcome in terms of the payoffs. That is not correct. These are the payoffs associated with the outcome. So your outcome must always be written in terms of strategies. So the outcome is aggressive. Is the Nash equilibrium of this game a dominant strategy equilibrium? Motivate your answer fully. Okay, so yes, it is. And the reason why we can say it is a dominant strategy equilibrium is because both players have a dominant strategy to play aggressive, no matter what the other player chooses to do. So in this answer, you've answered the question with a yes or a no, maybe if the question had asked for that. And you've said what the dominant strategies are, and you have defined a dominant strategy. So for the 3 marks, you would have to answer the question, yes or no. That's the first part of the question. And then motivate would have to involve you being able to say, you know what the dominant strategy is, and you know why it is a dominant strategy. Okay, so that's where the 3 marks would have come from. The umpire of the match wants to introduce a fine for any teams that play aggressively. How large would the fine need to be to ensure that tactical is the only Nash equilibrium in this game? Okay, so let's first off just look at the problem. Why would we even consider tactical as an outcome of the game that we would want? So why might we not be happy with the outcome aggressive? Awesome, yes. So tactical is optimal because it gives the highest total utility. This is suboptimal, right? If we compare aggressive to tactical, we see that this is Pareto inefficient. Tactical represents a Pareto improvement over aggressive. Awesome. So how could the umpire find these two teams in order to get tactical to be the outcome? So essentially, what we want is we want aggressive to no longer be a choice in this game. So how would we get that? Let's say if the Super Kings play tactical, what kind of fine would you need to introduce to take this payoff down so that tactical would be chosen as a best response to tactical rather than aggressive being chosen as a best response to tactical. So a fine aims to bring that number down. So what type of fine would make tactical best response over aggressive? Awesome, Geordie. Any fine greater than 8. Perfect. If the fine was larger than 8, so let's draw that out. Let's say the fine is 9. So it can be any number larger than 8. If we introduce a fine of 9, then how our numbers will change is as follows. So we have tactical, aggressive, and then we have the kings and the capitals. So tactical stays the same because the fine is only being applied if there's aggressive play. So if we fine 9 on aggressive play, then this 23 over here would become a 14. And then the 5 would remain the same because they're still playing tactical. If they play tactical, they're still going to get a 5. But if they play aggressive, it's now going to be 23 minus 9 is 14. And then if they both play aggressively, the total payoffs in that case will be -1, -1, because it's going to be 8 minus 9. Now, if we solve the game, we would see that if kings play tactical, capitals would be playing tactical as a best response, because 15 is more than 14. And then if kings play aggressive, they would also play tactical, because 5 is more than -1. If capitals play tactical, kings would choose tactical, 15 is more than 14. And if capitals play aggressive, kings are going to play tactical because 5 is more than -1. And so by introducing this fine, we end up at a Nash equilibrium, tactical, tactical. Okay, so any number larger than 8 would alter the payoffs to this game to make tactical, tactical the new Nash equilibrium. So the question says, consider the following ultimatum game between two players, Sindisiwe and Jane. Sindisiwe is given 1,000 Rand and must offer a portion of it to Jane. Jane can either accept or reject the offer. If Jane accepts the offer, both players get to keep their share of the money as offered by Sindisiwe. If Jane rejects the offer, neither player gets any money. Suppose Sindisiwe offers 300 Rand to Jane. What is Jane's best response if all she cares about is the money received in this game? In other words, her utility purely depends on the cash. And then you need to explain briefly what her best response would be. So the argument that is made is that her best response is to accept the 300 Rand. And I'm wondering if anybody in the chat wants to give a reason for why that is a best response. You don't have to write too detailed an answer. 300 is better than nothing. Yes, because the reservation option is 0. Yes, you're using perfect language. Oh my gosh. Okay, so if she declines, she gets nothing. Right. So the reservation option is nothing. That's the status quo. She already has nothing. And so if she accepts the 300 Rand, she makes economic rent. And so as a rational decision maker whose goal is to maximize utility, she would accept the answer. The two options in front of her are accept, don't accept. Not accepting gives her nothing, so accepting makes her better off than getting nothing. Awesome. What factors in the real world might influence a responder to accept or reject an offer from a proposer? So in the real world, there are other factors that dictate whether or not we're going to accept these kinds of offers besides the money. Can anyone think of a reason why she might not accept this offer, even if it gives her money when previously she had none? What might be a factor? Fairness. Awesome. Yes. If there are government provisions, okay, so that's bringing in Unit 5. So yes, it might be that there are other outside options that make her better off than this 300 rands. Might want 50-50, yes, so that's fairness again. Reciprocity is another thing that could make her either accept or reject. So she might reject because she believes that this is going to teach the person about fairness. So you're going to reciprocate by being also unfair because, yes, spite. So spite is a type of reciprocity. Could we talk about the fact that no one would be better off if she rejected the money? So ultimately, her decision is only going to factor in her rent. So she might accept the offer of 300 rand because she thinks it's fair that everybody gets something. So for example, if this person only offers her 300 rand, she could be spiteful and reject it, or she could have a sense of fairness where it's like, well, if I don't feel great about only getting 300 rand, I prefer 500 rands, but if I reject it, then this person also gets nothing. And so with a sort of sense of fairness, you might actually accept it just because you feel better that at least somebody's better off. Yeah, so you can accept it because even though the other person might get more than you, because you don't like the idea of no one getting nothing. Reciprocity. So reciprocity is like tit for tat. So when you're reciprocating, you're doing something in kind. So if somebody gives you a bad offer, you can reciprocate by then rejecting it. So someone's put in the chat, reciprocity in which two people or groups perform mutual corresponding actions based on the actions of the others. Perfect, exactly. So it's like you're matching that other person. So spite is another reason. Is bargaining an option in this situation? No. So in these ultimatum games, we would argue that it's once off. If we did allow for repeat, then there may be some bargaining. But in terms of answering this question, just assume that this is a once-off thing that's happening. So it's not going to happen again. Okay, so fairness, reciprocity, spite. Linked to fairness could be a preference for equality, or we could also say an aversion to inequality. So all of these are types of social norms or social preferences. So there's sort of guiding institutions, typically informal institutions. So just like saying please and thank you. Altruism, yes, altruism is also there. Yes. Okay, so these are all different types of social norms that guide the way that we behave in social interactions with each other. Do you only have to give 2 in the question? Yes, you only have to give 2. So you wouldn't have to give a full list. Okay, so you get 1 mark per factor given.